All right, here are the answers to the mental math. We have a division problem with one negative sign, so the answer is going to be negative. And it's 360 divided by 8. Now so 8 times 4 is 32. So yeah, 8 times, basically 4.5 times 8 is 36. So 360 or 45 would be, anyway, tricky one. Good job. Okay, 2.5 times 4 is actually, I think about 25 times 4 is 100, or 2.5 times 4 is 10. However, and so it would be 10 to the 10 times 10 to the 5th, but 10 is not an appropriate scientific notation, so it's 1.0 times 10 to the 6th. Okay, this one, we subtract 1.5 from both sides, so when we do that, we get 5. So 2c equals 5, so half of 5 is 2.5. Okay, converting 0.02 kilograms to grams, we move the decimal place over twice. 1, 2 to get to, no, 3 times, 1, 2, 3 to get 20 grams. All right, this one we do 4 times 3 is 12, and 4 times 3/4 is 3, so 12 plus 3 is 15. 33 1/3% more than 60. What that means is a third more than 60. So a third of 60 is 20, and it's going to be a 20 more than 60, which is $80. Okay, now we're going to jump into the lesson. We're going to talk about scale. Now yesterday, we did similar triangles and how it's the same shape, different size. And we also use this idea for scale models and scale drawings, you know, like when, well, we'll talk about a few of them, but it's used especially in floor plans and building buildings, because you don't, if you want to draw something out on a piece of paper, you need to shrink it down to fit on your piece of paper. And so we use a scale. Okay, so a scale of a model, the scale is always stated as a ratio. Okay, so if a model airplane is 1/124th the size of an actual airplane, the scale would be 1. Here's one way you would see it, 1/24, or you would see a scale like this. Okay, which means for every if a model airplane, that means the model airplane is 1/124th of like a full-size airplane. Okay, we can use a ratio box for these. And so let's look at example 1. A model airplane is built with a scale of 1/24. If the wingspan of the model is 18 inches, the wingspan of the actual airplane is how many feet? Okay, so we could do this way using a ratio box. Scale and actual, maybe, or they call it measure. Okay, so this is, you put the model and the object. So object, I don't have an eraser. Okay, so if the scale, the model is 1, the object would be 24. Okay, and the actual, they're saying the wingspan of the model is 18 inches, but it's okay if it's different. We're going to be using inches and feet, and that's okay. Then, because we'll talk about converting it. So we want to know how many inches the object really is, the airplane. Okay, so the model is 18 inches. How big is the actual airplane? Okay, and what we're going to do is get it in inches, but they want us to know how many in feet. So we're going to do a conversion at the end. So we set up our ratio, 1/24 equals 18 over, they did W for wingspan. Okay, and then we cross product, W equals 24 times 18. Now I'm going to give you the answer to that because I have it right in front of me. Wow, or, good job, 432 inches, okay? So it's 432 inches can go in our box, but they're asking, you always have to be careful You got to look at the actual question. That is not the final answer because I want to know how many feet. Now we can do it the way we've learned earlier, is do it with our unit conversions. 432 inches times, we know there are 12 inches in 1 foot. Okay, so there it is set up like that. And we can cross out our inches. And we just basically need to figure out how many times 12 goes into 432, because you're going to end up with 432 over 12 feet. And I'm going to give you the answer to that. It's 36 feet is how big the airplane is, the wingspan. Chad is molding a car from clay. Oh, I was going to say too that the book gives you a graphical, I didn't show it to you, and we're going to do one like it, a graphical display of the relationship between the measure of an object and the scale model. So you can look at the graph on page 676. Okay. Example 2. Chad is molding a model of a car from clay. So we're going to do model, object, scale, measure, and here we go. The scale of the model is 1 to 36. Okay. The height of the car is 4 feet 6 inches. So I could go ahead and say 4 feet 6 inches in here, but let's not have two different units in here. So first we're going to convert 4 feet 6 inches into just inches. Here's one way you could do it. 4 feet times 12 will give us how many inches plus 6, right? So that's 48 plus 6, so we've got 54 inches is the height of the car in real life. Okay, so I'm going to go ahead and put 54 in there, and M for model, so we're going to set that up as a ratio. 1 to 36 equals M over 54. Cross product, 36M equals 54. As you see, we're going to probably get a fraction, right? So we're going to divide both sides by 36. And so we get M equals, now we can first reduce 54, 36. 9 goes in there, 6 times and 4 times, but that wasn't far enough down. Half of 6 is 3, so 3 halves. Okay, now this is real life. So even though we said that we can keep things as improper fractions, when you're actually trying to determine the size of an actual object, it would be better to put it into a mixed number so it makes more sense. Okay, so that means 1.5. And that means our car, the scale, if we draw it to scale, the car should be 1.5 inches tall, our model car. Okay. And now we've got this idea of scale factor. This is weird, okay? Scale is stated as a ratio. Now we're going to talk about this thing called scale factor. The scale factor is the number of times larger or smaller the terms of one ratio are when compared with the terms of the other ratio. Okay, so that might not have meant anything to you with what I just said, and that's okay. Let's talk about this idea, okay? So, why did I write 3/4 here? Oh, okay, because it's in the book. The scale factor is the number of times blah, blah, blah. The scale factor in this proportion is 6, okay? Here's a proportion, and the scale factor is 6, and let's see why. Because all the terms of one ratio multiply by 6 to get all the terms of the other ratio. Okay, so it's the number of times one is larger or smaller to the other. Okay, example 3 is actually not very difficult. We're going to use scale factor. Instead of finding cross products, we're going to use scale factor to determine n. Well, what is the scale factor in this ratio. It is, if you're watching next to me, hold up number of fingers. What's the scale factor? In example 3, yes, it is 5. So the scale factor equals 5 because each of these terms multiplied by 5 will get this ratio. So 3 times 5, so 7 times 5, n equals 35. Okay, now let's use this idea of scale factor with these similar triangles. We've got triangle A, triangle B. Okay, if we multiply the length of one side of the smaller by the scale factor, we'll get the length of the corresponding side of the larger triangle. So 16 times something equals 20, 12 times that same something equals 15, and 20 times that same factor will equal 25. So all of these numbers multiplied by the exact same factor will give us these numbers that correspond. Okay, so we might want to, we're looking at this and we need to know the scale factor. Okay, so the way the book says it is they write dimension, you can go ahead and write this, dimensions of triangle A times the scale factor, I'm going to say SF, equals, and we're going to dimensions of triangle B. Okay, so let's just select a pair of corresponding sides. Okay, let's take 20 and 25. Those are corresponding. So 20 times something equals 25, right? Or how we would write it would be 20 times scale factor equals 25. And now we can figure out how to get that scale factor by dividing both sides. So our scale factor is 25 over 20. And that reduces to, 5 goes into there, 5/4. Okay, so the scale factor is 5/4 or 1.25 or 1 1/4. Okay, so those are our actual answers. It's just what are we multiplying everybody here by to get the dimensions of the bigger triangle. Okay, now we're going to go on and talk about, there's pictures of this, and we're talking about surface area, but the book has some pictures if you want to peek at that to help understand this. Okay, in this book I will say they're going to express scale factor in decimal form, so the answer that we just got here, they're going to want scale factor in decimal form, so 1.25 is actually the more appropriate answer for what the book is looking for, or this text. Okay, so we have two figures, a 2 by 3 by 4 and a 6 by 9 by 12, and basically we want to know the scale factor because these are similar. What is the scale factor? So let's just pick two corresponding sides. So it's 2f equals 6, whoops, so 2 times, obviously that is going to be 3. The scale factor is 3. Okay, now the area of any face of the larger prism, so let's check the areas here. The area of the small equals of any face. So let's take the front of the small front is a 2 by 3. That's the area, centimeters squared, right? If we do that with the big, the front of the big, our area is going to be 6 times 9, which is 54 centimeters squared. Okay, so how many times is the smaller area to the bigger area? So let's go ahead and say 6n equals 54. Divide by 6, and we get n equals 9. Okay, 9 times bigger, or 9 times the area of the smaller one. Okay, so let's try it with volume. So this was a 2-dimensional scale factor, and then the 3-dimensional, if we do the volume of the small, it's length times width times height, okay, which is 2 times 3 times 4, which is going to be 24 centimeters cubed. And if we do the big, we get 6 times 9 times 12. And what that gives us is 108 times 6, which is actually, I'll just give it to you, 648 centimeters cubed. Okay, so those are the volumes compared. And what is this, how much bigger is this volume than the smaller one? So we 24F equals 648, divide both sides by 24, and F equals, when we divide that, we get 27 times. Okay, we kind of talked about this in class once, how when we do one-dimensional, the scale factor is 3. Then we get to two-dimensional and we square the original scale factor, 3 squared. And then three-dimensional, we cube the original scale factor, which is 3 cubed is 27. So there's actually a really cool pattern here, if you allow yourself to digest that. Okay, so we are going to now jump into the practice. You can shut me off if you would like, and come back and check my work. All right, here we are with the answers. I'm going to go ahead and do them. You can tune me out if you are in the presence of my voice right now. The blueprints were drawn to scale 1 to 24. So here we are. And we've got model, object, scale, measure. The length of the wall on the blueprint was 6 inches. So a blueprint is the model, right? So 6 inches there. What's the actual length in feet of the wall? Times 24, which I'm going to go ahead and try. And that's inches, 144 inches. But we want it in feet, so 144 inches, 12 inches, 1 foot. So our final answer is 12 feet. Is the length of the wall in feet. Okay. Example letter B. Brett is carving a model ship from balsa wood, which is kind of a cool thing if you ever get a chance to do that. And set up our ratio box. 1 to 36, and his actual ship is 54 feet, but we want to know how many inches. So we're probably going to get, we could either change this into inches first, which I highly recommend, or you could do it after. So I'm going to do 54 feet into inches. Okay, so what we're going to have to do is 54 times 12, which is kind of a big one. We get 648 is how many inches? So I'm going to say 648. Now you could have done this the other way, and that's all right. So we're going to set this up. 1 to 36 equals m over 648. So 36m equals 648. Divide both sides by 36. And I actually have already done that, so I'm going to get m equals, oh, maybe I haven't done that. Let's check it out. Divided by 36. We get 388. Not 388, sorry, 288. So 18. So the model ship should be 18 inches long. Sorry, there was a lot of math there. I think if you did it the other way and converted at the end, it actually turned out better. Okay, these ones are not bad. We multiply, the scale factor is 3. So that means W is 21. Here the scale factor is 7. So what we get here, x equals 6. Okay, now these two rectangles are similar. Calculate the scale factor from the smaller to the larger. Okay, so 10 times f equals 25. Divide, so f equals 2.5 is the scale factor, and you can always check that. Is 4 times 2.5 10? Yes, it is. Okay. Now the area of the larger rectangle is 250 millimeters, right? And the area of the smaller one is 40 millimeters. So the area of the larger is how many times the area of the smaller? So we're going to set it up like this. And we get f equals 25 divided by 4. Well, that won't go in perfectly, and we are dealing with decimals, right? So go ahead and you can divide that if you'd like this way to get an accurate decimal, because it looks like it's going to go out 2 places, right? Okay, so 6.25 is how many times larger. Okay, now letter G. Fun. The scale of the car model in example 2 was 1 to 36. That means 1 inch on the model corresponds to 36 inches or 3 feet on the actual car. Make a graph like example 1 to show the relationship. Make the units of the horizontal axis represent the car. So we're going to say, right down here, just like in that picture, we're going to say actual size in feet. Okay, so we want to label. And then on the side, we're going to say model in inches, right? We're going to title it. So we've labeled the axis, and then we're going to title it. Let's call it scale of model car. Okay. All right, so we know that for every 1 inch is 36 inches here, but this is in feet, so every 1 inch here is 3 feet. So we're going to have a dot right here. So 3 feet on the actual car is 1 inch on the model. Okay, and that means we would go 2 inches is actually going to be 6. 2 inches is going to be, 72 inches, and 72 inches is actually 6 feet. And once we have 2 points, we know it's going to follow that linear pattern. And so we know at 9 feet, and we got 9 and 3, 12 and 4, and there we have our line. And then we can connect it. Yeah, it won't line up with the 0, 0. Not everything goes through 0, 0. So here's what happened and why it didn't go through 0, 0. It should go through 0, 0 with a proper graph, but what I gave you here had a problem. This should actually be 1, 2, 3, 4, 5. It jumps up to 2 right away, which was a mistake on my part, but here's how we can solve that in the graphing world. What you do is just go, remember that? And it means we're starting a little late. So this graph will actually, if it continued down, it would be 1 1/2 and 0, and it would hit 0 out here, but this shows us that there was a break between 0 and the first data set, okay? And that's okay. So if you do that, mark it covers up that error. Okay, so that's it for lesson 98.